Hello, folks. This is Dr. Faruqi again, and we are talking about the survival analysis. And we already talked about the parametric method, non-parametric method for the survival analysis. And today we're going to talk about another method, which is called semi-parametric estimation method for the survival analysis for the time to event data. And let's see what we have today. Folks, the linear regression can be used to quantify the effect of one or more predictor variables on a continuous scaled response variable, right? So your dependent variable, or you can say your outcome variable or response variable, is on a continuous scale. And this involves specification of a linear model for your outcome variable. Similarly, in logistic regression, your response variable is dichotomous, right? Yes, no. And we want to see the effect of one or more predictor variables or covariates or independent variables, you name it. So in logistic regression, this involves specification of linear link. You can call it a logit, remember, in a logistic regression, right? In the same manners like that, in a semi-parametric estimation method, several models are used to quantify the effect of one or more prognostic factors or variables. I will use the word prognostic for independent variable, for predictor covariates, right? So uh, in all my presentation, instead of using predictor or independent variables, I will use a word prognostic variable. And we want to see the effect on the time to event response variable or outcome variable or dependent variable, right? There are different methods to do that, but I will focus only one method today, and that is called Cox proportional hazard regression model. So just a second, give me a second, bear with me. So I just wanted to, okay, Cox proportional hazard regression model. A Cox proportional hazard regression model proposed by Sir D.R. Cox in 1972. This is a statistical technique for exploring the relationship or association between the survival time with several prognostic variables or factors or covariates, you name it, right? Okay, so a Cox proportional model provides the estimate of the treatment effect on survival time, right? After adjusting for other prognostic variable, like in your multiple regression analysis, you account for other variables and you want to study the effect of uh, a given variable, right? In addition, it allows us to estimate the hazard ratio, right? Remember, in logistic regression, we use the odds ratio, right? We estimate the odds ratio, which is easy to interpret. And similarly here, we will see hazard ratio we will use to estimate. And this is, and we already explained the concept of hazard rate and hazard ratio. And if you go back to see my presentations, and you will get all those concepts. So uh, in addition to estimate the treatment effect, we will see, we will estimate the hazard ratio, which is easy to interpret. All right. So what is Cox proportional hazard model equation? Suppose uh, you have a response variable or dependent variable or time to event or sensing, whatever you name it, and you have a bunch of predictors or prognostic uh, variables or factors that could be discrete or continuous, right? It depends on your study. Then the Cox proportional model equation involve the specification of log hazard, right? In logistic regression, remember the link was a logit. Here the link is log hazard. Like this is your hazard rate at ith subject, and you take the log of that, right? So that is your uh, like a link function which is associated with this equation, where this is hi, and if you can take the exponent of both sides, you will get this model where what is this? This is a constant. This is your baseline hazard function, and this is a positive value. We will also interpret this also. And this part is a non-parametric part. That's why it's called a semi-parametric method. This part is, the regression coefficients. You already familiar with that. So this is basically the overall is a semi-parametric method. So in this case, this constant is a baseline hazard function, and uh, how you can interpret that? Very simple. Uh, the hazard function for the population of subjects when your all prognostic variables are 0. Remember, in your simple linear regression, when you say y is equal to a plus bx, what is a? A is basically your average value when all your uh, the independent variables are 0. So if you say y is equal to a plus bx, so a is the expected value of your response variable when x is equal to 0, which is in mathematically you say y-intercept. But in regression concept or in conceptual way, you don't need to interpret that, because most of the time you will see that interpretation of that a doesn't make any sense. If you want to know, go to see my regression analysis presentation, and I explained over there with example. So this equation can be written as this, very simple, where this is your baseline hazard involved t, right, but not x. And this is your exponential function involve all x's, all your prognostic variables or factors, but not the t, the time, right? All right. So how we can estimate and interpret, right? Folks, there's this estimation method. It's all mathematical derivation. I don't want to discuss this because this is not a mathematical, like this is just a general concept I want to give you guys. uh, but I don't want to give you all the proofs and all the details in this short presentation. So the model parameters are these, and this can be estimated using the semi-parametric maximum likelihood estimation approach. We can we already say we can write this, the model, that do some mathematics, and you will see if you take the log both side, this goes away, put this here, subtract these, then take the log out, it will become the ratio, and this is your final model, right? After doing some mathematics, right? So what this model is just like y is equal to beta 1 x1 plus beta 2 x2 and so on. This is like a multiple regression model where this beta gives you the change in this, average change in this due to 1 unit change in your x1 variable, keeping all other variables constant, right? So that's the interpretation of that. The coefficient beta I is the estimated change in hazard. So this is the hazard function, your hazard ratio, right, of the event at time t after adjusting other factors. Now, if the beta is positive, right, there is an increase in hazard or risk of the event, occurrence of event at time t, right? So in other words, that decrease your expected survival time, because hazard and survival, they are reciprocal, right? If the hazard increase, survival decrease, and vice versa. Similarly, if your regression coefficient is negative, that will decrease your hazard ratio and increase your survival expected survival time, right? Expected mean survival time. And the ratio of the estimated risk factor, we call it a hazard ratio, right? uh, that can be examined to The likelihood of the folks, we have two groups. So we already explained it. I don't want to go again. But basically, hazard ratio is the ratio of two groups, right? One is your study group and other is your reference group. And the ratio one tells you there is no association between, there's no difference in like your study group and reference group. Go back and please look at it again. I will this explained in the real application. So that here is the interpretation of all what you need, and that's your take home message. So rate varies from 0 to infinity, right? If your hazard is decreasing, it varies from 0 to 1. If the hazard is increasing, it varies from 1 to infinity, right? So this provide the strength of association between the prognostic factors and the time to event response variable. Very simple, similar interpretation as you did in your logistic regression, uh, as you did in your linear regression or Poisson regression, right? Or quantile regression, whatever. All right. So basically, the hazard ratio is the exponent of beta I, and you can write it as this. Take the exponent, you will get the hazard ratio. For example, if your regression coefficient is 0.75, take the exponent, you will get this. So how you interpret it means the expected hazard of an event, occurrence of an event at a time t, particular time, very important, is almost twice as likely with an increase of 1 unit in your predictor variable or prognostic factor, right? If the hazard ratio is 0.5, it means there's equally likely, right? The change is equally likely. And if the hazard ratio is 1, it means there is no association between your prognostic variable factor, you can say, and your response variable, which is time to event, right? Okay. Now the once you are doing your analysis and you will see if the hazard ratio, you calculate the hazard ratio and you construct a confidence interval and you see it's a wide confidence interval, right? So keep in mind, if you have a wide confidence interval, it means there is a problem with your prognostic factor and your model or hazard ratio is not reliable, right? However, if your p-value is less than 0.05, you know that there is a statistically significant association between your prognostic factor and your outcome variable, right? At 5% level of significance, right? And if the 95% confidence interval or hazard ratio includes 1, this tells you no significant difference in hazard at the time t between the study group, right, and those in the baseline group or reference group after adjusting the other factors. So it's easy, it's not a big deal. Let's take an example. I took this example from internet. I read this example. I don't want to read this. Is all statistics. Is not a big deal. My response variable is time to death, which is like all kind of all causes of mortality. That's our event. So we have age, which is a continuous scaled prognostic factor, and we have another variable which is sex, and we are interested in male as compared to female. These are two groups, right? So what we'll see which one is the base. All right, these are the just a descriptive statistics. You can see that. All right, so what we did is what they did, not me. Sorry, they developed a model and they found. I'm sorry, I think I missed that. Hmm. Let me see. Yeah, here it is. I'm sorry. So here is the uh, the estimated parameters. So for the age, this is your beta, and this is your p-value. For the male sex, this is your again a beta, and this is your p-value. So this tells me both the factors are significantly associated there with the outcome variable. And let's see how we can interpret these. Very simple. If there is 0.11949 unit increase in the expected log of hazard, right? Because go back and see it's a log of hazards of all case mortality. That's your outcome variable for 1 unit increase in age. So unit here for age is year, so I will use a year. If it's a month, it would use as month. So 1 year increase in age holding sex constant. So age is a continuous variable, so it will be interpreted as I said. But sex is a dichotomous variable, so we have to take one as base and compare with other. So I think women we take as a reference group, and male we will take as they took as a study group. So there is this much unit increase in expected log hazard of this for men, right? That's your study group compared to women holding age constant. So interpretation of these two, you will see there is a log this is a little bit difficult. Let's take the hazard ratio and it will make so easy for you guys. Take the exponent and see there is almost 12% increase in the expected hazard of this with 1 unit increase in age, right? Very simple. See, similarly, if you take the exponent of this tells you the expected hazard of all cause mortality uh, in is almost 20% higher in men, which is your study group, as compared to woman or female, which is your reference group holding age as constant. So that's just two variables. But if you have tons of variables, so they did that. They have like they have other variables also, and they have blood pressure, smoker, these are other prognostic factors they include, and they estimated with p-value 95% confidence interval or hazard ratios, right? So it's very simple, very easy interpretation. Like let's see how we can interpret these. So first of all these factors where you can see the p-value less than zero point 0.05, they are your significant factor at 5% level of significant. As you can see, there is an association between these prognostic factor and all cause mortality, right? All right, and what is this? uh, the factor that are not statistically significant, we cannot say for sure they are not associated with the the your outcome variable. Maybe the sample size is a factor, maybe the confounding factor make them non-significant, right? So you have to dig down and further analysis you have to do that, but right now it's not a time to do all the discussion. Now you can see these are the factors, right? These are the prognostic factors that are associated with all case or cause mortality. Now since 95% confidence interval does contain one, what does it mean? It means there is a statistically significant association. Statistically significant association. We don't know the practical situation, we don't know the practical significant or clinical significant. This is just a statistical significant, right? Clinical significant, practical significant is something else. So right now statistically we can say there is a significant association between age, sex, all these prognostic factor and all cause mortality, right? Similarly you can say other two factor, you will see they does contain one. So there's not statistical significant association. You know why? Because you are testing odds ratio is equal to 1. That's your null hypothesis. If you contain the null hypothesis, then you accept your null hypothesis. If it does not contain, you reject your null hypothesis, right? So basically that's your acceptance region, you can say. So assumption, these are some assumption for the Cox proportional hazard model. It's not a big deal. You can go by yourself. If you have any question, let me know. Right? I don't want to go into detail. Let me know if you have any question. Right? Similarly, we have another model, accelerated failure time model. I don't want to go in this too. So this is our reference. If you have any question, let me know. And thanks for the watching. And this is all our this conclude our survival analysis. So this is just a basic idea I gave you in 456 presentation. Because sometimes people ask me how we can do in SPSSR. Folks, this is a complete, a big course. It takes 4 months, 6 months, even a year to complete that. So please don't expect 5 4 presentation of 20-minute length cover everything. No, just idea that I'm giving you the conceptual idea. So right, if you have any question, let me know. Thank you very much for watching, and you have a wonderful